Hello, I'm Karan Taneja, and in this video I'm presenting my paper titled A Bayesian Deep CNN Framework for Reconstructing KT Undersampled Resting-fMRI by me, Prachi Kulkarni, Professor S.N. Merchant and Professor Suyash Awate, all from Indian Institute of Technology, Bombay. In this paper, we aim to achieve higher spatial resolution in resting state fMRI without increasing the scan time by undersampling during the acquisition and then reconstructing using our novel CNN framework. There are two CNN components in our framework that are jointly learned. First, CNN is used to fill in missing k-space points, that is, missing frequencies, and second CNN is for image quality enhancement in the spatiotemporal domain. Results are very promising, and I encourage you to see the paper for many more details, reasoning, and experiments that are not given in this presentation to save time. The figure on the right here shows how we retain the central k-space, which contains lower frequencies, and randomly sample lines outside it. We also undersample in time. We also add noise to simulate the acquisition noise. Our CNN has three stages as shown here: stage 1, stage 2, and stage 3. The first stage takes in the left and right parts of the k-space separately and passes them through two different 3D CNNs denoted by phi left and phi right here. The filled parts and the middle part are combined to give the complete k-space. Stage 2 applies 2D Fourier inverse transform to convert k-space to image domain. We further upsample this in time using simple linear interpolation. The third stage passes this crude approximation of the fMRI image through another 3D CNN for quality enhancement. This CNN is denoted by psi beta here. Psi m and psi s are two channels which denote the mean and standard deviation estimate from the CNN. In standard mean square loss, we assume that the variance is constant, so we ignore the psi s. You can see more details about the network in these three tabs. We experimented with several variations that use three different kinds of loss functions. First is simply the mean square loss. Second is what we call the robust loss, where instead of using the usual p equal to 2 in this equation, we use p equal to 0.5 for example, which comes naturally when you assume generalized Gaussian distribution on the output error instead of Gaussian distribution that mean square error assumes. The third one is the Bayesian loss, which is derived when we assume different variance for each voxel and time point in the image. The red and blue term here are the mean and standard deviation estimates that we discussed earlier. The green term, however, is an intermediate term which is shown here. We found that an intermediate loss term greatly increases the training time. The ground truth for this intermediate term is simply obtained by subsampling the original image in time. We use four variations. First is SCNN, or the shallow CNN, which has two layers in both phi and psi and uses mean square error. DCNN, or the deep CNN, has 4 layers instead of 2. RDCNN, or the robust deep CNN, is deep but uses robust loss. Similarly, Bayesian deep CNN, or the BDCNN, uses the Bayesian loss. We also have 4 baselines. First is RA-DICT, or the robust adaptive dictionary method, which uses a data adaptive sparse dictionary optimized using the robust loss idea. WAVE is simply a sparse wavelet model on spatiotemporal fMRI signal. Low-rank applies a low-rank model on k-space versus time matrix to fill in the missing values. BD-MRI-T, or Bayesian Deep MRI for time, is our adaptation of a CNN-based dynamic MRI reconstruction method. Again, you should look up paper for more details about these baselines and the corresponding papers. Here we see the mean structural similarity box plots over all the evaluation subjects and all network maps. BDCNN clearly outperforms all of them. BDMRI, T, and RA-DICT are good among the baselines, but none of them are at par with the proposed CNN framework. Images from dorsal attentive network are shown in this slide. Even visually, we found that BDCNN is closest to the ground truth. You can find images for default mode network and executive control network maps in the paper. In this visualization experiment, we treat the standard deviation estimate from the BDCNN as estimate of the uncertainty in the mean output. We also plot the artifacts introduced due to undersampling by taking the difference between original and zero-field reconstruction. We observe that uncertainty map from BDCNN has similar patterns as the artifacts. The figures can be seen here. These are the original data points. These are the corresponding residual, and these are the uncertainty map obtained from the phi s output of our model. It suggests that framework is able to capture the error patterns due to undersampling quite well.